Okay, so today we're going to talk about inequalities in one triangle. Our I can statements for today are: I can recognize and apply properties of inequalities to the measures of the angles of a triangle, and I can recognize and apply properties of inequalities to the relationships between the angles and sides of a triangle. So I've already pre-filled some of this slideshow in just because it's going to be a longer lesson as is, so we're trying to cut out as much time as possible. Just know that you might need to pause this video multiple times to be able to write down all your notes. So take your time, make sure you take good notes, because this can be a very confusing lesson. That being said, our first thing is the definition of an inequality. Their words here are just very poor in my opinion, so I would rather take the opportunity to just look at the example. So the example here says if 5 equals 2 plus 3, then 5 is greater than 2 and 5 is greater than 3. Which, if we think about that, it makes sense, because if 5 is the same amount as those two quantities, so quantities of 2 and quantities of 3 added together, then it's going to be bigger than each of them individually. So when I think of this, I think of it kind of like a balance, right? So let's see if I can draw that. So we have kind of our balance here. And let's just say we have, let me erase this. So let's say we have, I don't even know how big. Let's say we have a let's just say we have a, let's say we're not on the eraser. Let's just say we have a sandbag that is 20 pounds. So let's say we have this sandbag, there's a little string. So we have a sandbag that's 20 pounds on this side. And then on this other side, we have two little 10-pound weights. So if these are equal, then this is going to be a balanced, happy balance. So right now it's all balanced and happy. But if we don't keep those two weights together and we keep the sandbag on, let's just say we keep one weight on, one little dumbbell, and then we have our 20-pound sandbag. Well, that sandbag's going to be heavier, so it's going to make that balance go down. So if we have two parts that make up the same quantity as a bigger piece, and we take away one of those parts, then it's going to be less than the big quantity. I don't know if that example will help or hurt you guys. It works in my head. But if it's easier to work with the numbers instead of the example that I drew out, we know 20 is bigger than 10, and we know 20 is bigger than 10. But if we add 10 and 10 together, we know 20 is equal to 20, is essentially what this is saying. Now, if we look at this next page, we have our comparison property of inequality, transitive property of inequality, addition property, subtraction property. These are very similar to the transitive, addition, and subtraction properties we've done before. The only real difference is now it is of inequality instead of equality or of whatever, congruence, all those good things. But it's the same general concept. It's just getting a little fancier now. So that being said, the comparison property of inequality, what it says is that if you have two real numbers, then one of them is going to be smaller, A is less than B, they're going to be equal, A equals B, or one is going to be bigger, so A would be greater than B. So if we chose any two numbers, one of those three statements is going to be true for it. So the first two numbers I chose were 6 and 2. Okay, well 6 is greater than 2. Next set, 6 and 6. 6 is equal to 6. And then our third set was 6 is less than 100. So 6 is smaller than 100. So no matter what two numbers you grab out of thin air, it doesn't matter. One of them is going to be bigger and one of them is going to be smaller, or they're going to be the same exact number and they're going to be equal to each other. This is just basic inequalities, just like you've done 100 times since you were in second grade probably. Now the transitive property of inequality, what that says is if A is smaller than B and B is smaller than C, then A must be smaller than C. So my example here was, well, if A is a real teeny tiny number and so A is 0.1, and then if we say B is 7, well, yeah, A is smaller than B because 0.1 is smaller than 7. Then if we chose an even bigger number for C, then we could say B is less than C if C is 9. Well, and if A is smaller than B and B is smaller than C, then A, of course, has to be smaller than C as well. So that's transitive property. Addition property, what this is pretty much saying is, there we go. Nope, stop. There we go. So what this is pretty much saying is if we have two numbers, so A and B, if A is bigger than B, then A plus another number is going to be greater than B plus that same number. So the examples I used here were A is 5, B is 3, and then C is 10. So if we said 5 plus 10, which would be 15, and B, which is 3, plus 10, then 15 is still bigger than 13. That was terrible wording. So if 5, I don't want to draw the whole balance again, so I'm not going to. But essentially, if we had a 5 and a 3, that's opposite. See, and that's why I shouldn't have drawn the balance again, because I was going to draw it wrong. So if we have a 5 and we have a 3, then the 3 is going to be lighter, so it's going to go up on the balance. Now, if we add in 10 pounds on each side, the only thing that's going to change is that whole piece is going to be a little bit heavier. The balance is still the same. You still have more weight on that left-hand side. That's all this addition property is saying. And then the subtraction property is pretty much saying the same thing, except for the opposite. So let's say we have 10 pounds, and let's say we have 5 pounds. So the 10's heavier than the 5. If I take away 4 pounds from each of these, so this would be 6 and this would be 1, the 6 is still heavier than the 1 because we took away the same amount on each side. It's just like when we're balancing equations. If we do the same thing on both sides, then nothing changes. Okay? Moving on. This is our first big piece here. So we have the exterior angle inequality theorem. So what this says is the measure of an exterior angle of a triangle is greater than the measure of either of its corresponding remote interior angles. So essentially what that says is we have our exterior angle 1 down here, and then we have our two opposite interior angles. So we have A and we have B. So what this is saying is angle 1 is going to be equal. it's going to be bigger than A and it's going to be bigger than B. Now, if we think about why that is, last chapter we had the exterior angle theorem. And what that said is, in this case, angle 1 is going to be equal to, where did that go? So I still have that. Oh, stupid thing. So angle 1 is going to be equal to A plus B, which brings us back to our initial little definition of an inequality. So what this says is, if angle 1 equals A plus B, then angle 1 is going to be bigger than B by itself, and it's going to be bigger than A by itself. So we're going to get into a little bit of application on this. This is one example problem, but it is an absolute mess when I worked through it, so I don't even want to confuse you guys with that. Now, this one, on the other hand, is a little bit more manageable. So what our goal is in this example here is they want us to list all of the angles whose measures are less than angle 4. I would absolutely love to tell you that you could just go in and say 3 looks less, 2 looks less, 5 looks less, 6 looks less, 8, 7's less, 1 looks less. I'm not so sure about 9. I'll just leave that one. I wish we could do that. That would be lovely if everything was drawn to scale and we could just measure it, but we can't. So we have to use our exterior angle inequality theorem. So if we use angle 4 as our exterior angle to start with, we can say right off the bat that it's bigger than angle 2 and angle 5. So we know angle 2 and angle 5 are going to be in this, which is great. That's a good start. So we know, let's put that. So we know angle 4 is going to be bigger than angle 5 and angle 2. So now the next thing we want to do is we want to see if there's any other angles that we can prove. And this is where it gets a little tricky because there's a lot of angles here and it's hard to say what we should look at next. So looking at this, we could say, well, 9 is bigger than 8 and 6, but we have no way to relate the angle of 9 back to angle 4. So that wouldn't really be the route we want to take. Angle 2 isn't an exterior angle for any triangle, but angle 5 is. So let's look at angle 5. So we have, I'm going to outline this in black just so we can see it a little bit better. So we have this triangle with angles 6, 7, and 8 inside. This equilateral looking triangle here in the middle. And then we have 5 as an exterior angle for that. So we could say angle 5 is bigger than angle 8 and bigger than angle 7. Now, so we know 5 is bigger than angle 8 and angle 7, and we know angle 4 is bigger than angle 5, which by transitive property means that 4 is also bigger than angle 7 and angle 8. Now, as far as the other angles, I don't think we can prove any of the other angles are bigger or are smaller. Even though it looks like they are, I don't think we can prove that to be true for any of these other ones. So I think we'll have to stop at B. Going on to our next problem, they say use the exterior angle inequality theorem to list all of the angles whose measures are greater than the measure of angle 8. So we want anything that's bigger than angle 8. Let me find something here to color in angle 8. So angle 8 is this lovely little angle here. Okay. So we need to find all the angles that are bigger than angle 8. Now, looking at this, I know angle 4 and 5 are going to be bigger than angle 8 because, well, they're listed in every single answer. Now let's try to show that though. So angle 4, where is it? Oh, okay. So angle 4 is bigger than angles not the eraser. It's bigger than angles 2 and 5. And then we know 5 is going to be bigger than 8 and 7. So by that logic, 5 is bigger than 8, and 4 would also be bigger than 8. Now let's check and see if any of these others are going to be bigger. What about 9? So 9 over here on the left-hand side has to be bigger than angle 8 and angle 6. So 9's bigger than angle 8 as well. So we know our answer is going to at least be C. We might be able to get to D. Let's look at angle 1. So looking at angle 1, I can see that angle 1 is bigger than angle 3 and angle 7. However, I don't think we can prove definitively that 1 is bigger than 8. Because then we could also say 4 is bigger than 7. But that doesn't tell us anything without knowing the angle measures. So our answer would have to be C. All right, so exterior angle inequality theorem. The concept is not wildly terrible, but the application of it can be a challenge. That being said, I understand it can be a challenge. We're going to have to try our hardest. And it would be a really good thing to ask questions on if you're having struggles. Maybe say, this is what I got. Do you think we can find more? Or something along those lines. Try your best on all of them. Then when we go over the homework, then you'll want to check your answers. You'll want to have your homework done so you can check your answers when we go over it. So you know if you're missing some, if you're putting too many, and then we can troubleshoot kind of what patterns are going wrong. That being said, let's move on to the second half of this lesson, which I believe is the easier part. I don't even know if I want to say easier, just the more logical part to me. So on this second part of the lesson, we have angle side relationships and triangles. So what this says is if one side of a triangle is longer than another side, the angle opposite the longer side has a greater measure than the angle opposite the shorter side. And then this 510 says if one angle of a triangle has a bigger measure than another angle, then the side opposite the bigger angle is longer than the side opposite of the lesser angle. I have a really good visual for this. I'm going to post it as a separate video because it's on the computer instead of the iPad. So check out that video to kind of see why this is true, and we have a manipulative to work with on that. But essentially, if you think of it, if you take two pencils in your hand and you kind of make the angle between, if you connect them at the eraser and then you make the angle smaller, you can see the tip of those two pencils, or that opposite side, gets shorter and shorter. And if you separate the tips of those pencils and you make that angle bigger and bigger and bigger, then that side gets longer and longer and longer. So that's kind of the example and why you can, or in how you can see that this works. Or this is true, I should say, not that this works, it's true. So the application of these problems actually isn't wildly terrible. So they want us to list all the angles of ABC in order from smallest to largest. So what I want to do first, I'm going to say, okay, this is my biggest side, or from smallest to largest. So this is my smallest side. That means C is my smallest angle. This is my next smallest side. That means A is my next smallest angle. This is my largest side, so B is my largest angle. I know I went pretty quick through that one, but I think we may have got it based on the lack of hands I'm seeing raised in this video where I'm doing it in an empty classroom. All right, so once again, list the angles in order from smallest to largest. So our smallest side, 17.4, so X is my smallest. Then my next smallest is 18.5, so T is my next. And then finally, V is my biggest side, so A is going to be my answer. And moving on, list the sides of ABC in order from shortest to longest. Now this is where it gets a little more difficult, mainly because we have to write a little bit more. So my shortest side is going to be opposite my smallest angle. So the side opposite 45 would be side AC. So line AC. Then my next one would be opposite 55, which would be line BA. Then my final one would be line BC. We got to write a little bit more on that, but once again, I have faith that we can handle it. List the sides of RST in order from shortest to longest. Once again, shortest, 222 RS. Second shortest, RT. Third, ST. My handwriting is getting bad because I'm moving a little bit quicker, but it's whatever. So Ebony is following directions for folding a handkerchief to make a bandana for her hair. After she folds the handkerchief in half, handkerchief in half, the directions tell her to tie the two smaller angles of the triangle under her hair. If she folds the handkerchief with the dimensions shown, which two ends should she tie? So essentially, which two angles are the smallest? Well, 22.6 is bigger than 16 and bigger than 16, so I would say my two smaller angles are going to be opposite those 16s. So I would want to fold angle C, angle Z, and angle Y. Cool. So Tanya is following the directions for making a kite. She has two congruent triangular pieces of fabric that need to be sewn together along their longest side. The directions say to begin sewing the two pieces of fabric together at their smallest angles. At which two angles should she be sewing? So the smallest angles are going to be opposite our 1.5 sides. So one of them would be angle D, and one of them is going to be angle A. So angle A and angle D. Lovely. All right, so I know this one can be a challenge. If you have any questions, please don't hesitate to reach out. I'm happy to help you out in the afternoon or whenever you have time.